Hi everybody. As you're hopefully getting some more practice on stoichiometry problems, we need to throw in an additional consideration, what's called a limiting reagent problem. These problems often kind of make people take a pause, and the questions that I usually get are twofold. One is, how do I solve a limiting reagent problem? The other one is, how do I even know when a problem is a limiting reagent problem? And so I wanted to use an example here of combustion. We could use, again, any chemical reaction we wanted to. Combustion is always the reaction of a fuel with oxygen to produce combustion byproducts. In the case of a hydrocarbon fuel like octane, reacting with oxygen will produce carbon dioxide gas and water vapor. I've already balanced this reaction for us. A typical stoichiometry problem here might say something like, how much carbon dioxide in grams is produced if I burn 123 grams of octane. And that's a typical stoichiometry problem. And we're going to solve this with the same 3 steps that we always use. And that is, step 1, we will convert our starting material to moles. So that's our grams on the bottom here to moles on top, using its molar mass from the periodic table. If we add up 8 carbons and 18 hydrogens, we get something like 114.25 grams for every mole. Step 2 of our stoichiometry process is, again, always converting moles of what we're starting with to moles of what we're trying to answer the question about, in this case carbon dioxide. I get these numbers from the balanced reaction. So I see in the reaction that every 2 moles of octane that I burn produces 16 moles of CO2. And then thirdly, step 3 always answers the question. So we get out of this mole unit of our desired material and we answer the question. In this case, we want grams of CO2. And if we add up a carbon and 2 oxygens, we get that every mole of CO2 gas is 44.01 grams of that material. And so as I do the math across, I can see that my grams of octane will cancel in step 1. And then my moles of octane cancel in step 2 as I do that divide by 2 operation. Times 16 on the top of that fraction, I'm now at moles of CO2. And moles of CO2 will cancel when I finish off here and get to grams. And I find out that burning 123 grams of octane will produce 379 grams of carbon dioxide. That's taking my 123 divided by the 114 number, times 16 divided by 2, and then times 44 in that third bracket. If this was all the question asked us, we'd be done. We'd say burning 123 grams of octane can produce 379 grams of CO2. That assumes that I have enough oxygen to do this. And so you might picture that we're burning this octane, and we could use that as a stand-in for gasoline. We're burning gasoline in an open environment. So we have a beaker or a bowl of gasoline sitting on a table someplace, and we're setting it on fire. Where does the oxygen come from? Well, it comes from the atmosphere. There's plenty of oxygen circulating around that dish, presumably, to be able to burn all of the octane. That's not the case if we talk about this process happening inside of a closed container. And for combustion of gasoline, the first closed container that comes to mind might be an engine cylinder inside of a car's engine. It's not open to the environment. Whatever air gets in there comes from a purposeful injection of air through valves, through a mechanized process. So we need to consider that one of the 2 materials, either the octane or the oxygen, could run out first, depending on the mixture that we end up with in that closed container. So what I've just shown you is a typical stoichiometry problem. Where it becomes a limiting reagent problem is when we're given a quantity for both reactants. So let's rewind and pretend that the problem said, how much CO2 can be produced in grams if 123 grams of octane was reacted with 47.8 grams of oxygen. Now we have a starting amount for both reactants. Now, one of them is going to run out first. And the way we're going to figure this out is just to do the same exact stoichiometry, but starting with each reactant. So I've already done the octane line in blue. Now I'll go down below, and we can do exactly the same sort of a three-step process using the other reagent. So my same 3 steps, I'll convert starting quantity to moles in step 1. I'll convert moles of that starting material to moles of the material I'm asking about in step 2 using the balanced reaction. And then I will convert moles of that material to whatever unit it is that I want at the end. So you'll notice this third bracket is exactly the same as the bracket up above, grams of CO2 per mole. What'll change here, of course, are the first 2. So when I add up the molar mass of oxygen from the periodic table, remember it's 2 oxygen atoms per molecule, so 32 here instead of 16 grams per mole. And then from the balanced reaction, I look up top and I find out that every 25 moles of oxygen that reacts produces 16 moles of CO2. And now I'll go through and do the math just the same way that I did before. I'll say convert here to get to moles of oxygen, 47.8 divided by 32. Then I'll do my mole ratio in the next step, so I'll multiply by the 16 on top, divide by the 25 on the bottom. And then my last step times 4401 gives me my mass of CO2 that could be produced here. So 42, I'll round to 3 significant figures again, 42.1 grams of CO2. Now what we have to do is say, how much CO2 can I actually make? The blue line says if I use up all of my octane, I can produce 379 grams of CO2. The green line says if I use up all of the oxygen present, I can only produce 42 grams. The lower of those 2 numbers, this is the actual amount of CO2 that these reaction conditions can produce. And this is what we call my theoretical yield. That's if the reaction goes perfectly, given those 2 amounts I started with, that's the most CO2, the most product I can hope to make. And the reactant that generated that theoretical yield, in this case the oxygen, that's what I would call my limiting reactant or limiting reagent. So now if I think about what's happening in this reaction, basically what I started out with was my little container here that had 123 grams of octane in it and 47.8 grams of oxygen in it, and the reaction happened. And now at the end, I still have some amount of octane left over. If I wanted to, I could calculate that. But I've used up all of my oxygen. It's gone. What I've made in its place is 42 grams of CO2. And if I wanted to, I could go ahead and calculate how much water vapor. It would just be a matter of changing that third green bracket, changing the moles of CO2 to instead read moles of water, and then changing that last bracket. This is the concept of limiting reagent. It's particularly important in real-world chemistry. If you were a designer working on an engine design, and this was the setup that you had, what does it mean? Well, it means that you're running out of air, you're running out of oxygen in that combustion chamber, and that means you're wasting fuel, because whatever octane is left over in the mixture at the end, that in a car would go straight out the tailpipe. So in mechanical terms, we say a car is running rich if it's not burning all of the gas. You can smell that gasoline vapor smell at the end. Conversely, if it were imbalanced in the other direction and we ran out of gas before we ran out of oxygen, you might say the car is running lean, that we need a little bit more fuel to get the maximum punch out of that performance. So how do I know it's a limiting reagent problem? Because I'm given starting amounts for both reactants. And how do I solve it? The same three-step process that we deal with every time we do a stoichiometry problem. We'll run through the problem starting with one reactant all the way to the product, and then start over with the other reactant all the way to the product. Whichever one of those product amounts is lower, we call that theoretical yield, and whichever material gave us that, in this case the oxygen, we call that the limiting reagent. Some problems will also ask us to calculate an percent yield for a reaction, and this is something we do in synthetic chemistry quite a lot to sort of measure how good a job we're doing. Percent yield is the actual yield that you made when you did the reaction divided by the theoretical yield, and then we express that as a percent. So in this case, if we were to do that with this reaction, the theoretical yield is that 42.1 grams of CO2 that I calculated a moment ago. The actual yield would be one that I had to actually measure. I have to actually do the reaction in a container and measure how much product I get. And so whatever problem you're doing would give you that number. And so let's pretend that this problem said I'm reacting 123 grams of octane with 47.8 grams of oxygen. Calculate the theoretical yield and the limiting reagent. And then it might say, what is the percent yield if the reaction is determined to have actually made 31.4 grams of CO2. I'm going to say this is from the problem. This is going to be a given to you. In the lab, you'd measure it on a balance or something like that. In a problem, this is going to be given to you as a number. So if we pretend that that's the number that the problem gave us, we would take 31.4 grams, divide by the 42.1 theoretical yield, and times 100. I get a percent yield here of 74.6%. How good is that? Well, it's okay. If I'm in synthetic chemistry, I'm manufacturing this for a purpose. In the case of our little engine example here, I'm not doing as well as I would like to, so I'd have to look at how the machine is working. In ideal chemistry, I'd like that number to be up over 90% if possible. And, a chemical engineer would go through and try to figure out how to change the method to make that number better. So stoichiometry problems are very real-world applicable. Limiting reagent problems are often the case if we're not dealing with sort of an open environment or an excess of one or the other material. So if you're given both starting amounts, solve using this process, calculate your theoretical yield, limiting reagent, and then if the numbers are given to you, you can calculate a percent yield. So keep up the practice and good luck.